we discussed about the generation of permutation of odd elements out of n. But the problem we told that it will not generate the permutation in lexicographic order. So today we like to first discuss about the problem of generating the permutation in lexicographic order. So to design that, yesterday or last class we just told that we have to design a new data structure, which is basically not new, it is a modified version of the balanced binary tree. Now, if we remember correctly, that balanced binary tree has the certain property that the height of the left subtree and height of the right subtree of a binary tree or binary search tree should be, if I take the difference between these two, should be either +1, -1 or 0. So from the definition or from the properties of binary search tree, the height of the balanced binary tree will be restricted to order log n. Right? So if it is the case that searching on the binary search tree will take order log n time, if I have to insert a node in binary search height balanced binary tree, then you can go to the last node or lift node in log n time, and then after insertion it may lose the property of balance factor, that is the ±1. So you may need to do the rebalancing so that the binary search tree becomes again height balanced binary tree. Right? Now here let us define a problem. Problem is that given there are m distinct records which form a height balanced binary tree, right? And there is the key k. Now the problem is to find a non-negative integer u. The problem is to find a non-negative integer u such that the rank of k plus u in your m records is u plus 1. So what it means that you have to find out an u which is a non-negative integer such that the rank of k plus u, if basically I want to insert k plus u in the records, m records, such that its rank is u plus 1. So rank of k plus u, if we insert in m records, is u plus 1. And once you get that k plus u, you insert in the height balance tree of m records. So insert k plus u in the height balance tree with m records, right? And once you insert it, it will lose the property of balancing. So you need to do the rebalancing. So this is the problem. Now, if you remember that in any height balanced binary tree, that a node consists of 4 fields. One is the left link field, another one is right link field, and the balance factor and key. Right? So a node consists of 4 fields. One is balance factor, which contains the value 0 or 1 or -1. Then left link, it points to the left subtree, and right link, it points to the right subtree. which is also a balanced one, and K is the key field where the data is stored. Right? In our case, this node structure has been changed. Instead of having the 4 fields, here we are keeping the 6 fields. The 6 fields are one is balance factor, one is key, one is left leg, one is right leg. And here I am putting another info is Li and Ri. Li is the left subtree information field. And Ri is right subtree information. Now what it means, what I want to tell to Li will give the information about the number of nodes in the left subtree. Ri will give the information about the number of nodes in the right subtree. So if I have a node here, so you may have other structure here and so on. So to know the number of nodes in this subtree, I can find out Li plus Ri plus 1. That will give you the total number of nodes in this subtree. So the problem you can define or you can redefine into 3 sub-problems. One, I have to find out the rank of K plus U, right? That means I have to find out one such U such that the rank of K plus U is U plus 1. Once you get that K plus U, you have to insert that K plus U in your tree, in your balanced binary tree, height balanced binary tree, and after insertion, it may lose the property of balancing, so you have to rebalance it. Since I have decided, since it is a binary search tree, and these M nodes or M records, they are distinct in nature, for any node P, the key of P satisfies this property. Right? That means the key of this node will be larger than this one, the key of this node, and smaller than this one. Now, what we know that height of this tree is log n, because there are m records, so height is log n. And whatever searching procedure you follow to find that you have to traverse from here to here, up to the leaf node, to take the final decision. So from here to leaf node, height is order log n. So you can easily know that, or easily show that to get such a u, it will take order log n time. Once you know the u, you can insert that node, a new node as a leaf node, and then balancing may be required. You have to do the balancing, which takes order log n time. So general procedure, see, I know this left information field. I know the right information field, I know the balance factor, and I know the key value of this node. Now, the k to be inserted, or k plus u to be inserted into this node, you try to understand this one, then either it will follow this path or it will follow this path. Now, if it follows this path, then at least this many nodes will be smaller than, all these values will be smaller than whatever you are going to insert, because k plus u will be in this side. Is it okay? Now, if it is that means u value will be at least this many nodes, right? And if it follows this path, then u value will be at this side, not this side. So what I do, that u will be this Li. Initially, I will think that u is your Li. Now you check k plus the Li is the left information field. If you find that this is smaller than your key value, k plus Li is smaller than this value, then the path to be followed this one. If you find that k plus Li is greater than or equals to this value, then you have to follow this path, right? And suppose I am here, then again your Li is this Li, k plus Li to be tested, and you follow this path or that path, and so on. Let us consider one example that will help you to understand how it works. Suppose I have 1, 2, 4, 5, 7, 8, 10, 11, 12, maybe 30. How many? 4 plus 10 data I have taken, right? 4 plus 4 plus 10. And let us assume that my tree looks like this. this is suppose consider this is a balanced binary tree of 10 nodes, and I want to, my k is set 2. My k is 2. Now how can I proceed? So what I told that if I have to follow this path, then there are 4 nodes at least you will have on the left of your k plus u. So here I start with k, u equals to 3, k plus u, u equals to 3, I get it is 5. Now this 5 is equals to this. So that is not ranked, you will not get u plus 1. So what you have to do? You have to follow this path. Okay? So once you are following the right subtree, that means the node will be inserted in this area, not on the left side. Once you are inserting the node in this side, then this node will be increased by 1, because node will be inserted to this side. Now what happens in that case? That your u becomes guaranteed 4, because at least 4 nodes will be there. Now you are here, so that contains 2. Okay? So k plus u is your 11. Oh no, k plus u is 6 plus 3, sorry, 6 plus 2, 8. 6 plus 2, 8. Right? Now you see that 8 is less than 10. So the path is this side. Right? So once you are following this path, this number will be increased by 1. Because now node will be inserted somewhere here. So it will be increased by. Now what is your u? U will be still 4, because this side, it is not traversing towards the right, it is traversing towards the left. So it is, u will be still 4, plus expected one is 1, plus 1. K plus u becomes now 5 plus 2 is 7. Now 7 is less than 8. So the path will be followed this one. So your u is now 4 plus 0, k plus u is 6. So 6 is, so this will be increased by 1, which is 2. 6 is less than 7. So you got the position where to be inserted. This becomes 1. Right? And your u is 4. Okay? So what is happening? That means k plus u is 6. K plus u is 6, and the rank of k plus u is 4 plus 1 is 5. Because 4 of them are smaller than this, so k plus 1 is 5. U is 4, u plus 1. So rank of k plus u is 4 plus 1, 5. Now this, up to this is simple. Now the problem is coming, saying it loses the property of balance vector. Right? Now you could have done the rotation technique to solve this one, but only rotation will not help. Remember, I am keeping track about the number of left information, the number of nodes on the left subtree and number of nodes on the right subtree. So that information I will be losing. So you have to be very careful. See, if the rotation technique, if I follow, the basically it loses the property of here, right? This is it lost the property of balancing here. Yes? So this is simple, 7 will come, 8 will come down and 6 will go up. And correspondingly, while you are changing the balance factor, you have to change the information of the Li and Ri. So the total time complexity for this is order log n. So this problem I have solved now. The given n records, distinct records, which form the high balance binary tree and an argument k, you can always find a non-negative positive integer, non-negative integer u, such the rank of k plus u is u plus 1. And if you get that one, you insert k plus u into your high balance tree and rebalance the tree, and also adjust the left information field and right information field values, right? And this can be done in order log n time. Order log n time. So these data structures will be used to generate the lexicographic permutations. Let us assume that x gamma is the gammath lexicographic permutation of r elements out of n. So gammath lexicographic permutation of r elements. Let us assume that I know first m elements of x gamma. Let us assume that first m elements are known to you. I want to find out that what is the m plus 1th element. Let us assume these are a1, a2, a3, an. Now I have to find out what is am plus 1. So if I can find out that am plus 1, then I can make it for any m I can find out, and that will give me the lexicographic permutation x gamma. Now let A be the set of a1, a2, an. Now these permutations are obtained from first n integers, 1, 2, 3, 4 up to n. Let us assume that S is your 1, 2 set of n integers. And define V by S minus A. That means the set of all the elements which are in S but not in A. Right? Now my m plus 1th element, am plus 1, must be one of the element from B. Right? So that is the thing I have to find out. What is that element from B? Now we told that x gamma is the gammath lexicographic permutations, and its first m elements are a1, a2, an. So from the definition of the permutations, there are several permutations you will find whose first elements are a1, a2, an. There exist several such permutations whose first m elements are a1, a2, an. Right? And number of such permutations is n minus mp r minus n. n minus m p r minus m. So there exist n minus m p r minus m permutations whose first elements you will find a1, a2, a. Right? And x gamma is also one such permutation. So if I arrange them in lexicographic order, this n minus m p r minus m permutations in lexicographic order, then x gamma may be lying somewhere here. Okay? Let us rank them 1, 2, 3 up to n minus m p r minus m, and x gamma is lying here. Let us assume that x gamma m is the position from the top. Basically, instead of making it confusion with this, let us put it delta gamma m. Delta gamma m is the position of x gamma from here to this. So obviously, delta gamma 0 is nothing but your gamma.
So m variable we have taken was, so that will again, or
No, the m indicates the number of elements you have
the
already generated.
already done.
Number of elements. So there are m values you have already generated. These elements are a1, a2 here.
Okay.
Right? Now,
And the rank of x gamma is
rank of x gamma in this table
Yeah.
is delta gamma m.
Okay.
Delta gamma m.
Okay.
Right? And obviously delta gamma 0, when m equals to nothing has been done, the initial position is gamma. Right? Now, what is given to you? Given to you is delta gamma m, and also you have n minus m p r minus m. This is the given to you for different values of n. Now, one property in permutation, if you see that the occurrence of a mth element is am, and mth element is am plus 1, the number of such cases is same. Right? That means this n minus m p r minus m, you will be dividing into n minus m groups. Each group is having n minus m minus 1, p r minus m minus 1. In the last class also we discussed this one. So we divide this n minus m p r minus m into n minus n groups. Each group is having n minus m minus 1, p r minus 1, r minus n minus 1 permutations. Right? So let us assume that K is the group number for delta gamma m. Because to find out the group number, delta gamma m divided by n minus m minus 1 p r minus 1. And if you take the ceiling function, that will give you the group number of delta gamma m, which is K. Now since we are arranging them in lexicographic order, this K will help me to find what is the m plus 1th element. Right? This K is nothing but the kth smallest, because B is the set which contains all the elements which are not in A but in S. Right? So K is the, because I have to arrange in lexicographic order, K gives me the kth smallest element in B. Right? But remember one thing, that I don't have B, I have A. Because I have generated A1, A2, A3, A. So can I get the value of kth smallest element of B from A. So that is the, if I can do it, then I am through. Now let us assume that kth smallest element in B is say Bk. Let us see. Now remember one thing, that A union B is your S and A intersection B is phi. Right? And S contains the first and natural numbers. Now, if kth smallest element in B is Bk, then can I tell there exists Bk minus 1 elements smaller than elements in S smaller than Bk. Because this is the first and natural numbers, Bk is one of the element here. So there exists Bk minus 1 elements smaller than Bk. Elements in A smaller than Bk. Right? So if Bk minus 1 element smaller than Bk here and K elements are here, because in the K minus 1 element smaller than your Bk. Here K minus 1 elements in B smaller than Bk. Because Bk is the K smallest element. Bk is the K smallest. So there exists K minus 1 smallest element in B. K minus 1 element in B smaller than Bk. Right? So there exists one U here. Right? So that here one U and here K minus 1. So that these two addition will give you Bk minus 1. Right? So there exist U elements in A smaller than Bk. So that, such that U plus K minus 1 is equals to Bk minus 1. Right? K minus 1 elements in B smaller than B, K, and U elements, there must be some U elements in A which is smaller than Bk. So U plus K minus 1 is equals to Bk minus 1. That means U plus K is equals to Bk. What it gives you? That given K, I have to find out one U in A such that rank of U plus K is U plus 1. Right? So that algorithm, that structure we have to discuss. So I can find it out such a K, such a U. So if I know K from A, I can find out U. So that U plus K is equals to your Bk. So based on this idea, we can have to find out say X gamma. So initially n is equals to npr and delta is equals to gamma from the definition, and you have n is known to you and also r is known to you. Now for m equals to 0 to r minus 1, you first define your n. N is n by n minus m. So that will give you n minus m p r minus 1, r minus p, r minus n. Now K is nothing but delta by N, right? Yes. So if M equals to 0, that is first iteration, then your result is K. Result is, just take away K. Else, so result is K and insert in A. Else, find a non-negative integer U such that rank of U in A such that rank of K plus U is U plus 1 and insert K plus U in A. By insert I mean not only insertion, you have to do the balancing also. And now I got what is my, say, here basically U is 0, right? So I can write here AM equals to this, and here also I can write AM equals to K plus U, right? So that you got your A1, A2, and 3 AM, K plus U. Then you have to modify your delta. Delta is equals to delta minus K minus 1 into N. Right? So that you can find out the index of delta in the next, for next iterations. So this is, I think, all about your algorithm. So you observe that to obtain the gamma lexicographic permutation, you have to do the R iterations. And here you need the searching technique because you have to insert an element in a balanced binary tree. So at the mth iteration, the height of the balanced binary tree is log m because m elements are there, log m. So order log m, and there are order log m at the mth iteration, actually log m minus 1, let us assume log m. And it will be iterated r times. So summation over order log m, which is nothing but log r factorial. Log r factorial, because this will come m equals to 0 to r minus 1, and this is nothing but order log r factorial, which is nothing but order r log r. Right? So to generate one permutations, you need order r log r time. Right? Now there are NPR such permutations you have to generate, so which takes NPR r log r time. You observe that this algorithm is basically adaptive because it does not need every processor can do it on its own, right? So if I have the P processors, then the time needs to find out that NPR by each processor will be generating NPR by P permutations, NPR by P permutations, each processor will be generating. So the time needs NPR by P R log R. But if you see that it is not cost optimal algorithm. But they are very simple to implement. Let us consider one example that will help you to understand. Suppose you have n equals to 4, r equals to 3. And what is your capital N? 4p3. It is 24, right? So, and let us assume that number of processors is you have 50. P is equals to 50. So, let us see what the second processor will generate. Right? The second processor will generate. So, second processor will generate the second lexicographic permutation and 17. So, it will second permutation and 17th permutation. Right? Because you have the 15 process. So, second processor will generate the second lexicographic permutation and 17th lexicographic permutations. So, your delta value is initially second 2, then is coming, what are the parameters you need? What is your initial n? Initial is 24. So 24, your m is 0. So m value is 0. What is your n value? N value is n minus 4, which is 6. What is your k value? K value is 1 because 2 divided by 6 is 1, and since m equals to 0, so it will print 1. So your p will become 1, 0, 0, 0. This is your initially it will generate. Now, what is your delta value? Updated delta value you have to do it. Delta is delta minus k minus 1 into n. K is 1, so 0, delta is still 2. Right? So delta is 2, m is 1. What is your n value? N is 6 divided by 3, 2. What is k value? Delta by 2 is 1. What is your A? A is now, you have to insert 1 here, k plus u. So, k plus u, to obtain this, you see that I will be checking k plus u is 0, so is 1, 1 is this, so it will be left of it, so it will become 0, this side is minus 1, 1, 1, 2. So this is your, at the second iteration, and what will be the delta value? 2 minus k is 1, so 0, it is still 2. Right? So delta value 2, m is 3, sorry, m is 2. What is n? Delta divided by 4 minus 2, 4 minus is 2, 2 divided by 2 is 1, and k is now 2, because 2 divided by 1 is 2. Now this 2 to be inserted here. So 2 plus 0 is 2, 2 is greater than 1, so it will follow this path, right? So 2 plus 1, 3, 3 is greater than 2, so it will be inserted here. So you will be inserting here, but doing that, it will be losing the property of balance, so it will become now it will generate the all lexicographical permutation, because that is the ultimately you have to show, because this is the thing what you started. So in order to show that, first part I want to tell that whatever number it generates, the number will be lying between 1 and n, because that my set A and set B, they are belonging to the set of S, and S contains 1 to n. So one part is that all the numbers, whatever numbers it will be generating, that will be lying between 1 and n. Second part is that in the case of permutation, NPR permutations, that there are n blocks, or one block will contain first element 1, another block will contain second and first element 2, and so on. And the size of each block is fixed. That is n minus 1, PR minus 1. Now, in order to show that it obeys the lexicographic property, let us take the two permutation x beta and x gamma, and with the assumption that beta is less than gamma, right? So you have to show that x beta precedes lexicographically x gamma. That is the thing, that for beta less than gamma, you have to show that x beta precedes lexicographically x gamma, right? For beta less than gamma. Let us assume that both of them have generated m elements, first m elements. Both of them have generated first m elements, and they are saying the first m elements of x beta and x gamma, they are A1, A2, An. Right? Now, we have also defined delta beta m is the index of beta, x beta, within that group. And also we have defined delta gamma, this is known. And since beta is less than gamma, it obeys the property of this also. Right? Because this is just an index, so it obeys the property of this. Now, you will be dividing, or you have to find out the group number, which is given by delta beta n divided by n minus m minus 1 p r minus m minus 1 less than right? So once I divide, it may not obey this property, less than property. It may be less than or equal. Because this is a group number. So there may be several permutations, may belong to the same group. Let us assume that the group number of this division gives you K1. So K1 is less than K2. Now, if it is less than, K1 is less than K2, that means what? You will be finding a non-negative integer u, right, in S, K1 plus u. K1 is different from K2, and it will get the smaller value, because K1 is the smallest element in B. K1 is smallest element B, and K2 is smallest element of B. There are two distinct numbers. If K1 is less than K2, if K1 is less than K2, then K1 is smallest element in B is always less than K2 smallest element in B, right? Because K1 is less than, because B is the distinct numbers. So is the case with in terms of A. If I tell in terms of A, then also you will get, because they are two distinct numbers. So if K1 element is smallest element less than this, then it obeys the property of lexicography. So if it is, by any means, if it is less than, then there is no problem. But if it is not less than, if they are equal, then the issue is coming. Now let us assume that K1 is equal to K2. Right? That means let us assume that it generates all same numbers. Now through contradiction, I would like to show that it is not possible. Let us assume that you have generated the same A1, A2, An, and M is equals to, say, R. What is R? R is nothing but R minus 1 if R is not equals to N, and R minus 2 if R equals to N. That means, if I want to generate computation of R elements out of N, if R is equals to N, that means you want to generate the computation of N elements out of N, then whatever is the case may be, then I want to show that last two digits are fixed. I will come to an example, this one. Otherwise, last one digit is fixed. So let us assume that I have A1, A2, Am, we have the same, and M equals to R. Now, I can show N minus M minus 1 P R minus M minus 1 for this M value. For this M value, you can find out this is always 1. Just you put, when R equals to N, when R equals to N, R equals to N, M equals to R minus 2. R minus 2 means N minus P R minus M. M is R minus 2. So it is becoming 1P1, which is 1. Similarly, if you put when R is not equals to N, then you will find N minus R plus 1 minus 1, and then this is also becoming to be 1. So if A1, A2, Am, M equals to R, this value is 1. Now what happens in that case? In that case, you have delta beta M less than delta gamma M. You are dividing it beta M divided by N minus M minus 1 P R minus M minus 1 right? But this value is 1. This value 1. I have shown that this is 1. So this K1 is less than K2. And if K1 it is not possible, at least when capital R case, it is K1 is less than K2. And that means that K1 smallest element in B is less than K2 smallest element in B, and at least in the last capital R case, this will be defined. And so that will prove that they obeys the lexicographic computation. That means X beta precedes lexicographically X gamma. Now, this part you have to show now that what I am telling, that if R is not equals to N, then last element is fixed. And if R is equals to N, then last but two elements are fixed. So let us consider one example, say N is 5 and say R is 3, right? So if I have 1, 2, 3, 1, 2, 4, 1, 2, 5, then 1, 3, 2, 1, 3, 4, 1, 3, 5, and so on. Right? When R is not equals to, this is the R is not equals to N. What I am telling that when R is not equals to N, then each of them is having one group, because these are fixed. Right? They are belonging to the same group, but only one group size is 1. That is fixed. 1. That is the N minus M minus 1, PR minus M minus 1 is 1. This is 1, 1, 1. And when N equals to 4 and R equals to 4, you have 1, 2, 3, 4, 1, 2, 4, 3, 1, 3, 2, 4, 1, 3, 4, 2, 1, 4, 2, 3, 1, 4, 3, 2. And here you observe that once I have that N equals to 4, R equals to N equals to R, then after that R minus 2, this is R minus 2 case, R minus this case, and the R minus 1 and R minus R. So these two cases, it is fixed. See, it is 3 in 1, 1 group, because 1, 1 group. So group size is 1. N minus M minus 1, PR minus 1. Group size is 1. Right? So that is the thing, that is the basis of telling that even if it generates the same numbers up to capital R, M equals to capital R, but in this case it will generate the two distinct numbers which obeys the lexicographic preceding rule. Okay? So this is about the lexicographic generation of permutations where elements are not distinct.